Oh yay, I think my microphone's going to work. Fantastic. Well, so let's talk about the mean. Most people feel like they know the mean, they understand the mean. I don't know. We'll see. Okay, so again, I'm going to use a psychology example because that's what I do for a living, but you can imagine any kind of variable that you want to measure. So suppose we measure some psychological variable in a convenient sample of people, and let's just say extroversion, on a scale from 1 to 7. 1 meaning highly introverted, 7 meaning highly extroverted. We might get numbers that look something like this. First, before we move on, I'm going to quiz you a little bit on your measurement theory. Going back to the measurement theory video, what kind of scale is person? Do you remember? Well, person, of course, would be a nominal scale, right? So those numbers underneath person, those mean nothing, right? All they do is denote instances of something. But we could just as easily replace those numbers with names, letters, codes, anything we wanted. And they wouldn't mean anything. Here, let me click on my laser pointer. There we go. So, that number 8 there is not twice as much as 4 and half as much as 16. It's just an arbitrary symbol, really. So it's a nominal scale. And what about extroversion? What kind of scale is that? Well, if you remember back to your measurement theory, it's either ordinal or interval. It's definitely not a ratio scale, right? Because remember, a ratio scale has to have a true or meaningful 0. 0 means absolutely none of the stuff we're measuring. And this scale didn't even have a 0 in it at all, right? It went from 1 to 7, so it doesn't even have a 0. Certainly not a meaningful 0 that means none of the stuff. So it definitely couldn't be treated as a ratio scale. Most data analysts and statisticians, I think nowadays, are happy to treat that as an interval level scale. There's probably a few diehards who still insist that it's only ordinal. But for the most part, we're going to treat it today like it's an interval scale because you have to have at least an interval scale to calculate a mean. Means don't mean anything with an ordinal scale, since the distances between adjacent units in an ordinal scale are not all the same. Okay, so just looking at the data, I challenge you to say something interesting about extroversion. Stop the video if you must. Think about it for a minute. Say something interesting about extroversion just looking there at the raw data. All right, are you back? Well, one thing clearly that we can say is that people are scattered. They're distributed. Not everybody is exactly the same in their level of extroversion. Now, that may sound trivial, but I think it's actually a profound insight to realize that there are these distributions and that in these variables, the numbers aren't all the same. And characterizing that scatter or that distribution along the number line is actually a very important topic. We'll cover that in another video. But because everyone is not the same and the numbers are scattered around the number line, so we say that they are distributed, and we call the data a distribution. Let's learn our first statistic. Actually, this won't be our first statistic because we've already covered frequency. When I used to teach this as a class, it was the first statistic. N. So traditionally, in most places, you'll use a capital N to symbolize the total sample size. In this case, N is equal to 16. Sometimes we use a small n, but typically small n's are reserved for denoting group sizes within a larger sample. For example, if I take a sample and then I randomly assign members of that sample to multiple groups, I'll use a little n with a subscript to denote the number in each of those smaller groups. And big N I'll reserve for the total sample size. But some people do use a little n for total sample size. And of course, symbols are arbitrary, right? So you could use any symbol you wanted. Aside from knowing that people are variable, though, what can we say by looking at the raw data? It's kind of hard to say much by looking at raw data. We need a way to summarize these data, to distill down these 16 numbers for extroversion that we're looking at into a fewer set of numbers that have something meaningful to say about the data. So one thing we might want to know is just how much of this stuff that we're measuring, in this case extroversion, how much of this stuff is there in the sample that we took. So what we're looking for is a way to say where the distribution lies along the number line. But to get a single number, we need to pick a part of the distribution to characterize. Are we going to characterize the left tail end of it, the right tail end of it? It probably makes the most sense, especially if we're going to compare this to another distribution, probably makes the most sense to pick the middle of this distribution. So the center, where does the center of this distribution of numbers fall on the number line? Now there's a number of different ways that we can define the center, right? The absolute middle is something called the median, and we'll talk about that on another video. We're actually not going to talk much about the median in this video. But because we're looking for the middle, in general, these statistics that we're looking for are called measures of central tendency. They're also often called, mainly by statisticians, measures of location. And that kind of confused me when I first heard it, but what they're referring to is location along the number line, or location along the range of the measurement scale. So measures of central tendency or measure of location. Now, I'm sure all of you have seen the mean before. Even if you're brand new to statistics, well, maybe not. Maybe if there's some 4th or 5th graders watching this video, you might not have seen it before, but the most popular measure of central tendency, of course, is the arithmetic mean. All right, and so I've put an equation up there. I don't want you to freak out. Don't leave the video. Keep watching. I promise you I'll walk you through this. It won't hurt a bit. All right, so this is just the symbol, the Greek letter mu, which we use to symbolize the mean, the population mean usually. I'll get to that in just a second. Remember this symbol. If you're not familiar with this symbol yet, the Greek letter sigma, go back and watch my video on statistical symbols, and that will get you back up to speed on the symbolism. Remember what this symbol means is to add up. So this would be read the sum of. The sum of. And remember this little number down here on the bottom, the subscript I. You see the I here too. This is just our index subscript. And so that's just telling us from the first observation, from I equal 1, that would be x sub 1, the very first observation, starting there and ending at n being the sample size. Let's make that our last observation. So x sub n would be the last observation in the data. The sum from I equals 1 to n of x sub I. In other words, all this thing is telling you is add up all the numbers. Add them all up. And then divide by n, the sample size. All right. Greek letter mu. So this is the population mean. And as such, it's a parameter of the population. And there's a problem with using the parameter, the population parameter, and that is that as I've set up this scenario, this example, these 16 folks are not our population, right? They're just a sample. So what can we do if we don't have the entire sample? Well, I think it's probably pretty obvious to most of you what we do, right? We we estimate the population mean using the sample mean. So now we've switched symbols here. Everything here is exactly the same on the right side of the equation, but on the left we've just switched the symbol to the x bar. X bar meaning the sample mean. You could also use the letter m here. A lot of people use m to represent the sample mean. There's reasons when we get to analysis of variance why it's more convenient to use the x bar notation than the m notation. M notation is very awkward in analysis of variance because you start requiring multiple subscripts. Anyway, you don't need to worry about that. Just know that x bar or m represents the sample mean. All right, so try this. Try calculating the sample mean on these data. Stop the video and try to calculate the mean level of extroversion in this sample. I'll wait. All right, did you do that? I'll bet you didn't do that. Let's move on. All right, so first you have to sum up all the x's, right? So the sum of x from I equals 1 to n, the sum of x sub I. This is all of the x's in the data set right here, and that sums up to 64. Once you get that sum, it's very trivial to just divide that sum by 16, which is n, the sample size, and we get a mean of 4. So the mean extroversion in this sample is 4. All right, so why is it that the mean is the most popular measure of central tendency? Why don't we use median more? Why don't we use the mode more often? For you stats nerds out there, why not the geometric mean? Why is it that this arithmetic mean is the most popular measure of central tendency? Well, obviously it's pretty easy to calculate, right? But that's not really why it's popular. When we describe the distribution, we want there to be minimal error. And what do we mean by error? Well, what we mean by error is the difference between our estimate of something and the thing it estimates. So when we use the mean to describe a distribution, what we're saying is that the entire distribution is characterized by that number. We're saying that that number somehow summarizes the entire distribution. So we're saying all those numbers are like the mean. Now the degree to which any individual observation deviates from that number, that is the error. And we want to minimize the error. For example, we found a sample mean of 4. So what's the error between the mean and x sub 1? Well, which observation is x sub 1? Well, that's x sub 1 right there. So the difference between the mean and x sub 1, that's just going to be 2 minus 4. Right? So negative 2 is the error of x sub 1 with respect to the mean. And here, notice that I'm just using a couple of symbols here, x sub I to refer to the ith observation. In this case, it's the first observation, and x bar to refer to the mean. And I'm always going to label this column like this because that's going to get you used to seeing that label and then seeing the calculation that results in this number, because you're going to see this in a lot of our measures of variability, and you're going to keep seeing symbols like this in throughout statistics. And so the quicker you get used to this little piece of it, the quicker the bigger equation that this thing is a part of will stop being as intimidating to you as perhaps it is for those of you who are beginners. All right, so the very first error, the very first x sub I minus x bar is 2 minus 4, or negative 2. Now, calculate the rest of the errors, which, by the way, are also called, there's another name for errors, and that is deviations about the mean. Deviations about the mean. If you really are going to understand statistics and understand how people talk about statistics, you'll have to understand both of those terms, error and deviation about the mean. Try it again. Try this. Stop the video and calculate the rest of the deviations, and then come back. All right. Did you do that? Well, here are the rest of the errors. So here are all of the errors in the data with respect to the mean. And now, add all of those up. Use your hand calculator, use your calculator on your computer, whatever you got. Add up all those errors, and what do you get? What is the net error? Well, of course, if you add all those up, you'll get a net error of 0, right? There is no net error. There is 0 net error with respect to the mean. And in fact, the arithmetic mean is the only point in a distribution that is guaranteed to give you 0 net error. Other points in the distribution might give you 0 net error, but only if they're equal to the mean. So the mean is that point in the distribution with 0 net error. And that's why we like the mean so much as a description of the distribution. So that probably seems pretty simple. But as we'll see, well, not throughout this class because you're not taking this as a class, you don't actually understand it yet. And you'll see this when I continually ask you questions that are answered by the mean, and you can't answer those questions yet. So I'll ask you a question, and the answer that I'm fishing for is the mean, but you won't recognize that fact. That'll indicate that you're not yet understanding the mean. So the mean has several interpretations. There's a lot of, they're not contradictory, of course, they're all complementary interpretations, but there's several different ways to interpret a mean. So one way of thinking about the mean is as a summary of how much of that stuff there is per individual in the sample or population, where stuff means whatever it is you measured. In our example, we just measured extroversion. So if everybody were exactly the same amount of extroversion, but we had the same total amount of extroversion in our sample, how much extroversion would everybody have? Another way to think about the mean is as the true value of the thing that you're measuring, with the difference between a given datum and the mean as measurement error. So we've already called it error. So now we're just calling it measurement error. That is to say, if we had measured without any error, all of the measurements would have come back with that same value. But because there is error in our measurement, the mean estimates the true value, and the deviations about the mean estimate the amount of measurement error that we've got. There's also a physical interpretation of the mean. If you take each amount that you measured and represent that by a single weighted object of a constant weight. Let's say, apologies to my international audience, I'm in America, so we'll use pounds. You can just replace that with kilos. Yeah, kilos. But let's say a 1 pound cube, and you were to place those cubes along a plank according to the value of each datum, as I've got illustrated here, then the mean is the point on that plank where the plank would balance perfectly, where you'd have exactly as much weight on the left side of the plank as you have on the right side of the plank. Now keep in mind, I've got these numbers here to represent the numbers in the data. These don't represent weights, right? Every one of these squares represents a 1 pound or a 1 kilogram. That was the word I was looking for that I couldn't think of just a second ago. See? Not using the SI system. Terrible, terrible. Anyway, kilogram, 1 kilogram or 1 pound weight. Each of these weighs exactly the same. The numbers just represent where they fall on the number line. So if you were to lay those out on a plank like that, the mean is the point where you would get exactly as much weight on the left as you have on the right. So that's where the plank would balance. Okay, yet another way of thinking about the mean is the expected value. So the expected value from sampling an individual from a population is that value that would give the least net error over the long run, meaning literally an infinite number of times. And the mean is that expected value. So if I were to take a sample from a population of just one individual and measure that individual, and then I were to take another sample of one more individual, measure that individual, and I were to keep doing that for infinity, the mean of that, the population parameter mean in this case, because I'm sampling from a population, the population mean is that one point that would give me, over that long run, over that infinite number of repetitions of this experiment, 0 net error. Okay, so that is the end of the mean. Hopefully that gives you a little bit more intuitive understanding of the mean, and I'll see you in the next video.